I'd like to welcome you to today's webcast, an overview of the commercial envelope requirements of the 2009 International Energy Conservation Code, brought to you by the U.S. Department of Energy's Building Energy Codes program. For those of you who want AIA credit or to generate and print a certificate of completion, a link will be put up at the start of the Q&A portion of the webcast. Please make sure to write down the link very carefully and type it into your browser at the end of the event. We're very happy to have as our speaker today Eric Makela of the Britt Makela Group. Eric, please begin.
Thanks, Rose. As Rose has said, my name is Eric Makela, and I will be your instructor for today's session on an overview of the 2009 envelope requirements in the International Energy Conservation Code. There were a few changes made this year between the 2006 and 2009. We're going to be covering the code itself plus the changes that will appear in the 2009. Some of the changes are on the actual ASHRAE standard that was now referenced in the 2009 IECC, which is going to be ASHRAE 90.1-2007. There were several changes made to the building envelope table requirements, both for opaque envelope and for the fenestration requirements. We're going to be covering those. First of all, I want to talk about the overall structural change of the 2009 IECC for all of the code itself. There was a change that was put in that essentially says that if you comply with Chapter 5 of the IECC for the envelope, you must comply with Chapter 5 of the IECC for both mechanical and lighting. In the same way as if you comply with ASHRAE 90.1-2007 for the envelope, then you must also comply with ASHRAE 90.1-2007 for the mechanical and lighting requirements. So essentially, whatever you pick for one, you must comply with the requirements, and that is the standard of the IECC for everything. And again, this was a major change between the 2006 and 2009. In the past, some designers have chosen to select the ASHRAE requirements for the building envelope requirements, and the mechanical designers have chosen to select the mechanical requirements for an ASHRAE standard 90.1-2007, and the lighting designers have selected Chapter 5 of the IECC, and that was allowed under the 2006. Under the 2009 code, though, that will no longer be allowed. So this is something that will impact how you demonstrate compliance with the Energy Code. When we're talking about commercial buildings, and we're talking for Chapter 5 of the IECC, we're looking at building stock that is essentially considered anything other than 1- and 2-family residential, R2, R3, R4, 3 stories or less in height. So an office building, a retail building, an assembly are all considered commercial buildings, as are residential 4-story and above is considered a commercial building. Anything else that does not fall underneath these categories is considered a residential building. So that includes 1- and 2-family residential, multifamily 3-story or less, townhomes. Those things are all considered residential. So it's a clear distinction between commercial and residential. We're going to be focused today on the envelope requirements as we talked about, and that's going to be essentially Section 502 of the 2009 IECC. As an option, you can use 90.1-2007 Section 5, but we won't be talking about that in today's webcast. Chapter 5 of the IECC focuses on a specific building stock. Essentially, it's for the building envelope requirements, it's a building less than 40% of the gross wall area in vertical fenestration, and also less than 3% of the gross roof area in skylights. If you exceed 40% of the gross wall area, or 40% and above of the gross wall area, then you have to either use ASHRAE 90.1-2007 for the entire building, or you also have the option of using Section 506, which is the total building performance approach located in Chapter 5 of the Code. The total building performance approach is a performance-based approach that allows trade-offs between the building envelope, the mechanical system, and the lighting system in the building. And it's a specialized software that you can use. This approach is also available in ASHRAE 90.1-2007. Total building performance approach is typically used for buildings that may comply with LEED requirements. LEED for new construction uses a similar approach to demonstrate the basic requirements for energy. So those are your options, again, for buildings that exceed 40% of the gross wall area or 3% of the gross roof area and skylights. Typical building that will probably be somewhere in the 20 to 25% range. A big box store, like is shown on the left-hand side of this picture, is probably going to be less than 10% glass area. Obviously, the Mandalay Bay on the right-hand side would not be an IECC building, would have to comply with 90.1, 2007, unless you use a performance-based approach. The code requirements for the building envelope are based on climate zones. The colder the climate or the hotter the climate will basically dictate how much insulation or the type of glass that has to be put in the building and the properties of that. So, for example, you have climate zone 1, which is down here in the tip of Florida, all the way up to climate zone 7 in the lower 48, which is upper Minnesota and the northern part of North Dakota. Climate zone 1 is going to be a hot climate. Climate zone 7 is going to be a cold climate. Then you have climate zone 4, which is on the kind of on the west coast and also through the mid-range through the country. That's going to be a moderate climate. If you're down in Las Vegas, you're going to be down in climate zone 3. If you're in Seattle, you're going to be in climate zone 4. Chicago is going to be a climate zone 5. So based on, again, climate zone, that will dictate the amount of insulation and the type of glazing requirements. You also have the country split up into levels of humidity. You have marine, which is a marine C designation, dry, which is B, which is the western part of the U.S., and then you have A, moist, which is the eastern part of the U.S., and then you have the warm humid line, which is kind of the southeast. So going back to our city location, Seattle would be in a climate zone 4C, which would be a moderate climate, fairly cold climate actually, with a marine type of climate. Las Vegas is down at down in the tip of Nevada. It's going to be a climate zone 3B. Chicago will be a climate zone 5A, so you're getting a little more moist. And then if you're getting down to the end of in Dade County area in Florida, you're in climate zone 1, and then below the warm humid line, or 1A. These will all dictate the insulation requirements and types of glazing that are required in the building to meet the code requirements. One of the biggest distinctions that was made in the building envelope requirements for the insulation requirements for opaque envelope was the distinction between high-rise residential, which is 4-story and above residential, and all other residential, which are going to be office, retail, assembly, and those types of uses. And the column was put in there for all climate zones, and essentially the requirements for high-rise residential in the 2009 code are going to be more stringent than they were in the 2006 code. The primary reason for that this was put into the code is that the energy used for high-rise residential looks a lot like what a low-rise residential multifamily building would look like. In other words, we live in that building during the evening time and we're out of that building during the daytime. For commercial buildings, we're typically live in the building during the afternoon and morning hours, but we're not in it during the evening time. So the energy schedules for both those buildings are different, and it was actually fairly cost-effective to increase the insulation requirements for high-rise residential buildings. So this was a major submission into the code. If we look at the table, table 502.2(1), this represents the insulation values based on the type of assembly in the building. For example, it's split up into roof assembly, walls above grade, walls below grade, floors, and slab-on-grade floors, and then down at the very bottom are doors, which are typically opaque doors, whether it be a man door, a solid man door, or roll-up door, but those are opaque door requirements. Each of the categories has different types of assembly. So, for example, your roof assembly will have insulation entirely above deck, which is going to be a built-up roof system, metal buildings with R5 thermal blocks, attic, and other. Based on the roof assembly types, you find the climate zone you're building in. So, for example, if we're in climate zone 5, a building with insulation entirely above a roof deck would have R20 CI, or continuous insulation. That means insulation not broken up by any framing members. Attic and other, and we'll skip metal buildings for the time being. Attic and other will have a requirement of R38 in the attic and other. So a blown-in insulation or fiberglass fab in an attic assembly for a commercial building would comply with the code. The metal buildings, which would have an R19 requirement. And there's a separate table we're going to go to in a few slides, table 502.2 that will actually give us how to meet the metal roof assembly requirements. As you can move to the right, you see for metal roof assemblies, the insulation requirements start to double. We have an R13 plus an R19 for all other in group 6. R13 plus an R19 for all other in group 7, and for group climate zone 8, rather, R11 plus an R19. So the farther, the colder the climate, the more insulation is going to be required for metal buildings. Attic and other will be a similar thing. It's an R38 throughout and R49 in the colder climates. And insulation entirely above the roof deck, the insulation levels start to increase as you get colder. So you select your assembly type, you select your climate zone, and that dictates the amount of the R value of the insulation that's going to be required to be put in. For wall assemblies, we have mass wall, metal building wall. Again, that corresponds to the metal building for roof assemblies. Metal framed building, which would be a steel stud wall in a building, and then wood framed another. This section of the table works the same way as the roof assembly. The R values are for insulation R value in the cavity itself, except for the mass. The mass wall R value will actually be the R value of foam board insulation, for example, that's placed over the face of the mass wall, and mass, we'll define that later, but it's essentially a concrete masonry unit wall. Tilt-up concrete, those are all considered mass wall assemblies. So the R5.7CI is continuous insulation over the face of the mass wall system. All of the other ones, when we get down to wood framed and other, you can see when you get into climate zone 4, they require both cavity insulation and continuous insulation over the face of the studs. Metal building assemblies typically, or metal framed wall assemblies typically require a continuous insulation even in some of the warmer climates like climate zone 2 and climate zone 3. So the colder the climates, the thicker the foam board insulation that will be on the outside. Metal buildings will require double insulation levels, and we'll take a look at that when we look at table 502.2 for N2 a little bit later in the discussion. So select your wall type, select your climate zone, and that will dictate the type of insulation and where the insulation must be placed. For walls below grade, the definition of a wall below grade is slightly different than that of a residential building, which is greater than or equal to 50% below grade. This is 85% or more below grade. It's considered a below grade wall. In most of the climate zones, you can see the NR, which means there's no insulation required, except when you get into climate zone 4 marine for group R occupancy, and then you need foam board insulation. And in that case, this is considered continuous insulation placed over the face of the either the tilt-up concrete or the poured-in-place concrete wall or the CMU wall system for the below-grade wall. So select again your climate zone and determine what R value you actually need for that wall assembly. For floors, we have two different types of floor assemblies. One is a mass floor. Now, this is not a slab-on-grade. This is actually a raised floor, like a floor over a parking garage. That might be a solid concrete floor. And the option on that is continuous insulation, because that's the only place you can put that insulation. You also have the option of a framed wall or framed floor system, either wood or steel framed, and this is going to be insulating between the framing members. And when we, a little bit later on in the discussion, we'll look at the distinction between a wood frame floor and a steel frame floor, because in the colder climate zones you're required to have more insulation in a steel framed floor assembly than a wood frame floor. So select your floor type and then go ahead and determine your climate zone, and that will dictate how much insulation you will need for that assembly. For slab-on-grade floors, this is where one of the changes was made between the 2006 and 2009. Most of the 2006 requirements did not require slabbage insulation for unheated slabs. So that's a slab that essentially has no radiant floor system in or uninsulated ducts, which is probably the majority of the slabs being built right now. And with the 2009 requirements, the no requirement or the NR only goes to climate zone 4, all other, and everything else, for the most part, the slab edge must be insulated to the required R value, and then down or down and out for the required linear length. So, for example, climate zone 5, group R, would require an R10 insulation and 24 inches of that insulation. The insulation must start at the top of the slab, cover the slab edge, and then continue down to the top of the footing or go horizontally underneath the slab. But you have to have that insulation covering up the face of the slab. That's the critical piece on that. If you have a heated slab, then this is going to be a slab with radiant coils in it or an uninsulated ductwork running through the slab, you will always have to insulate the slab edge. And the requirements in that range anywhere from an R7.5 to climate zone 1 up to an R20 in climate zone 8. And then there'll be differences as far as the linear length of insulation for that slab edge too. But again, the slab edge insulation must cover the face of the slab, and then either run horizontally underneath the slab or run straight down, or you can actually install it horizontally away from the slab edge. So you have a few different ways of installing the slab-on-grade foundation insulation. For opaque doors, the requirement is going to be a U-factor for that door, either depending on whether it's a swinging door or a roll-up door. So again, a swinging door might be a metal door, metal man door leading out of the back of a strip shopping center, for example. Roll-up doors might be if you have a conditioned warehouse and you have roll-up doors going into that. Those doors would need a U-factor. Typically, in warmer climates, the requirements are not very stringent, a U value of 0.70. Colder climates, starting probably in climate zone 4, the U-factor for roll-up doors, for example, is a 0.50, which is about an R2. For swinging doors, the U-factor would be a 0.70, or in colder climates, a 0.50. So in colder climates, you'll definitely have to insulate the doors. In warmer climates, you'll have to make sure it meets the U-factor, but a U-factor of 1.45 in climate zone 1 is not a very stringent requirement, so it shouldn't be a problem to meet the requirements. So this is the R value table, and this only focuses on insulation R value for the opaque assembly. The next table that was inserted in the 2009 code is actually an assembly U-factor table. And the assembly U-factor also accounts for framing in the building. So it's insulation plus framing. So if your assembly does not meet the R value requirements by themselves, you can also calculate out a U-factor for the assembly. So for example, a metal, an insulation entirely above a roof deck is going to be a U-factor in climate zone 5, group R, of 0.048, and that is going to correlate to an R20 continuous insulation. So you either put in that or you actually calculate the U-factor for the assembly. So this gives you an option if you have a unique assembly type that doesn't quite meet the R value requirements, but overall that assembly will meet the U-factor requirements. And you can actually mix and match this. Parts of the assemblies in the building can meet the R value requirements for insulation only. Other parts of the building can actually meet the U-factor requirements for an assembly that can't meet the R value for insulation. So this gives you another approach that wasn't in the 2006 code requirements. We talked a little bit about metal wall assemblies and metal roof assemblies. And I want to show you Table 502.2, which actually gives you a key on how you build some of the assemblies that require double layers of insulation. So for example, let's say we want to do an R13 plus an R13 roof assembly if we're required to do it in one of the climate zones. The description of that is the first R value is for faced fiberglass insulation bats draped over purlins. The second R value is for unfaced fiberglass insulation bats installed parallel to the purlins. A minimum 3.5 thermal spacer block is placed above the purlin bat, and the roof deck is secured to the purlins. So this gives you a description of how to build an R13 plus an R13 roof assembly. Or you can do an R13 plus an R19, so you would replace the second layer of R13 with an R19. So based on the type of assembly requirements for insulation in the R value table, we can then go into this table to actually determine how we're supposed to build that assembly. Same with walls. When we come down into the wall assembly, we have a few different options down here. If we're required to have an R13 plus an R5.6 continuous insulation, for example, it'll say the first R value is for the face fiberglass insulation. That's installed perpendicular and compressed between metal wall panels and steel framing. The second rated R value is for continuous rigid insulation installed between the metal wall panel and steel framing or on the interior of the steel framing. So again, this will give you the ability to determine how to install the insulation and give you a full description on how to do that. So the R value table will tell you how much to put in, and this will tell you actually how to install that insulation. The other option you have for metal buildings is to go into the assembly U-Factor table and generate an assembly U-Factor for either your wall system or your roof system and meet those requirements instead of going into this R value table. For roof assemblies, I want to cover a few specific things that I did not cover when we rapidly went through the R value table. For one thing, you can't install insulation on top of the drop ceiling and count it for insulation. The insulation will have to either be placed underneath the roof deck, or you need a hard lid underneath that insulation to act as an air barrier. And there's really two reasons that you can't do this. The first reason is the code will require you to seal up the building envelope. And if your insulation is in contact with an assembly, that now becomes your building envelope. So in order to count this drop ceiling as the building envelope, you would need to seal up the ceiling tile and also any penetrations in that ceiling tile, like fluorescent lights and things like that. The second part of this is just a maintenance issue. Typically, someone might come up and need to do some maintenance work on top of the drop ceiling. They'll push the tile over, the fiberglass out will come flying. And I haven't seen anyone yet actually go and retrieve that fiberglass bat and neatly place it back on top of the ceiling tile when they're done with the work. So this just basically says don't use a drop ceiling, or you can't use a drop ceiling to comply with the code. The insulation either has to be on a hard air barrier, or it has to be basically placed up in underneath the roof deck, which is installed up there quite a bit. This diagram just kind of gives you an idea of how a metal roof system is built. You've got your metal purlins, you've got your thermal blocks on top of the metal purlins. You can see how there's a double layer of insulation. And this is kind of we've already covered a lot of this information, but this just kind of summarizes where you may need double layers of insulation. For example, climate zone 2 through 8 require 2 layers of insulation for all other type of assemblies. So all other are going to be assembly, retail, office, those types of buildings. And this will tell you climate zone 2 through 5 and marine 4, an R13 plus an R13. When you get into colder climates, you'll require R11 plus an R19, for example. As you may notice, there's not a double layer of insulation required for most Group R buildings. Typically, you're not going to see metal building assemblies like this used for Group R buildings. It doesn't happen very often. So you're not going to see a high-rise metal building, for example, for Group R. So this just summarizes what we talked about in the R value table slide that we're going. For mass walls, I defined the mass walls earlier on as concrete masonry unit, tilt-up concrete, those types of assemblies. The code actually defines them as walls weighing at least 35 pounds per square foot of wall surface area, or 25 pounds per square foot of wall surface area if the material weight is less than or equal to 120 pounds per cubic feet. This is going to be most tilt-up concrete, CMU, that type of thing will fall underneath the mass walls. And for mass wall insulation requirements, you're going to put the insulation on the exterior of that mass wall. Now, for climate zones 1, or for Group R and 2, all others, you can actually use integral insulation on the inside of the mass walls, like a CMU block, and not have to insulate on the outside. And the criteria is set up here. Concrete block walls must comply with ASTM C90, and ungrouted or partially grouted at 32 inches. Ungrouted cells must be filled with insulation material of less than or equal to 0.44 BTUs per inch. This just gives you the criteria for when you do not need to put insulation on the exterior of that mass wall. Climate zone 1, all other, no insulation required for mass wall. So this is essentially the requirements for mass wall assemblies. Now, the one thing I do need to talk about here is that installing insulation continuously on the outside of the mass wall is not the only way to do that. You can also frame out on the inside. You can fur out on the inside with metal and wood or wood frame construction and insulate between the framing and comply with the metal or steel frame construction R-value requirements that are in the R-value table that we looked at. So you either can insulate continuously on the outside or meet the requirements again by either furring out on the inside or outside if you wanted to do that, installing insulation between the framing, and complying with either the metal or the metal framed or wood frame requirements in the R-value table for the applicable climate zone. So that just gives you another option on how to comply with the mass wall requirements. For wall R values, wood, metal framed, and other, we talked a little bit about insulation either must be placed continuously on the outside where it's required, or you could have continuous or insulation installed between the framing members. The CI, or continuous insulation, means insulation placed on the face of the studs and not broken up by any framing members. So essentially foam board insulation on the outside of a framed wall. This might be a synthetic stucco system where you're using foam board insulation on there. Anything that covers the face of the stud that actually has an R value of an R2 or better can be used and comply with this requirement. For metal building walls, we've already hit on this a little bit, but I wanted to bring it up again. Just so you can see the requirements in here, Climate Zone 1 and 2 and R16, Climate Zone 3 and 4, except Marine and R19, and then the colder climate zones will require insulation installed between the framing members and also continuous insulation on the outside. Now, one of the things to realize, too, is if you have a mass wall system, and you are in a cold climate, and the mass wall system requires both insulation between framing members, the framed wall system complies, if you have to have both insulation between the framing members and also foam board insulation over the base of the studs, that will have to be installed that way, going prescriptive. There's a way of trading this off using a tool like ComCheck, for example. You might be able to trade off the foam board insulation and just have mass wall with the insulation installed between the framing versus having the insulation between the framing and the foam board insulation. I haven't seen too many installations where you put in both foam board and insulation between the framing when furring out on a mass wall system. So that's a good opportunity to do a trade-off using a tool like ComCheck. For floor systems, we talked a little bit about the fact that you can have a mass floor. This floor in the picture right here is actually a concrete floor over a parking garage, or you can have a framed floor system. Maybe you have a floor, can't leave it out over the great outdoors, and you need to insulate between the framing on that. For a mass floor system like we're looking at in this picture, really the only place you can insulate on here is on the surface of it, or continuous insulation. So the code would require in this particular case that all insulation be placed continuously without being broken up by framing members if possible. Now obviously looking at this floor with the electrical running through there, that might be kind of difficult to do, but there are insulations that you can get that can, spray foam insulations and things like that you can use in floor assemblies like this. You have to just make sure that you comply with the evaluation service reporting and the code, the evaluation service reports, and also the IBC as far as placement of any kind of insulation in this kind of an assembly. So for mass walls, you have a couple of options for steel floor or wood floor type of joist systems. The insulation will be placed between the framing members. I talked a little bit earlier about the fact that for steel frame floor assemblies in some of the colder climates, you are actually required to have higher insulation levels than what is shown on the table. And footnote E to table 502.2 requires an R38 insulation in climate zone 6 through 8 for steel frame floor assemblies versus the R30 insulation for a wood framed floor system in those climate zones. So you need to pay attention to the climate zone and also what you're doing for framing to dictate how much insulation needs to be put in. The other thing is the insulation needs to be installed full height, so it can't be compressed. So that means the R38 insulation is going to need roughly 12 inches if you're doing a fiberglass bat, whereas an R30 will need 10 inches. So you definitely need to pay attention to the joist system that you're using to make sure that you're getting that insulation, again, full height in the joist cavity. For unheated slabs, we've talked about this a little bit. Essentially, this was a big difference between the 2006 and 2009. In climate zone 6 through 8 for unheated slab, you have to have insulation requirements for all other insulation. For Group R, it's climate zone 4 through 8. Again, Group R is going to be high-rise residential, so if you have dwelling units on the first floor, those floors could be very cold if they're slab-on-grade and the slabs are not insulated. So climate zone 4 through 8 for Group R, climate zone 6 through 8 for all other. If you have a heated slab, essentially you need to insulate in all climate zones. And again, a heated slab will have a radiant floor system, or it could have a uninsulated ductwork installed in the slab itself. Though that makes a slab a heated slab. And in that case, I believe all climate zones, you will have to insulate that slab edge. So verify the R value that you need and also the depth or the lineal length of insulation that you need to install on this. And again, that insulation must be placed over the face of the slab. And then you can run it down vertically after that, or horizontal under the slab, or horizontal away from the slab if you wanted to do that. So that's the end of the discussion for the opaque assemblies for R values. Now we're going to start looking at fenestration and glazing for the building. And there were some changes made to the fenestration requirement table. I've highlighted some of them. We're going to go ahead and walk through this so we can learn how to use this particular table if you're not familiar with it. Again, you're only allowed 40% maximum window wall ratio for a building. If you have greater than 40%, you either use a performance-based approach, Section 506, or you go to ASHRAE 90.1 2007 and comply with the entire ASHRAE standard. The categories you have to deal with are based on the type of glazing you have. The first requirement up here is for U-Factor, and it's for framing materials other than metal, with or without metal reinforcement or cladding. So this would be a vinyl frame windows. In some small office buildings like medical offices and things like that, the windows you install there look a whole lot like residential scale windows. And the U-Factor requirements for these windows are going to look a whole lot like the requirements for residential. The colder the climate, you'll have more of a low-E type of window. So from climate zone 5 on down, it's a 0.35 U-Factor window. When you get climate zone 3 and 4, climate zone 3 is a 0.65, climate zone 4 is a 0.40 U-Factor, climate zone 1 is a 1.2, so not a very efficient window. But again, this is Dade County, Florida, and then climate zone 2 is a 0.75. So really a double glazed window from about climate zone 2 on. So again, this is going to be for a manufactured type of window that you're going to just bring in and install out on site. For the next category is really for site-built windows, where you bring out the frame, bring out the glazing, and you install and build the glass out there. And you have a few different categories in here. One is curtain wall storefront U-Factor. We'll define a curtain wall storefront. I've got some. We'll define that a little bit later in the discussion. The curtain wall storefront will be it's a very common type of site-built window. And in this case, the curtain wall storefront must have an NFRC-rated U-Factor that meets the U-Factor requirements in the table. There is a default table within the code that you can use, and you can select a default value based on the frame type and glazing type to try to meet these requirements. But really, when you get after about a 0.60, I believe, U-Factor, you're going to actually have to have an NFRC-rated product. I believe, I'm not even sure of 0.60. I think 0.60 might be in that table. But the 0.5, the 0.45, and the 0.40 on curtain wall storefront will all have to be an NFRC-rated product in order to meet the requirements in this table for prescriptive. Again, the colder the climate, the more stringent the requirements are going to be for glazing U-Factor. Entrance door U-Factor, again, hotter climates, a 1.2 down to a 0.80 U-Factor for colder climates. Typically, entrance door U-Factors do not have as stringent requirements, primarily because of manufacturing constraints. They have to have the ability to take abuse and that type of thing. So the efficiencies for entrance doors, for glass entrance doors, are not as stringent as for curtain wall or storefront. If your glazing does not fall underneath the first category of essentially a vinyl framed window, or it's not curtain wall, storefront, or entrance door, then it falls underneath the all other U-Factor category. And this is going to be metal operable windows, for example, metal fixed windows that are manufactured and brought out on site. And you can see the requirements on those are a little bit, actually they kind of fall between the framing materials other than metal with or without thermal break and the curtain wall storefront glazing. So sometimes they're comparable, sometimes they're a little bit more stringent, or less stringent actually. So the all other is kind of a catch-all category that was for everything other than the site-built windows or the manufactured windows. Now I have two arrows of Requirement Zone 7 and Requirement Zone 8. And this is really where the changes were made in the code between the 2006 and 2009. The requirements actually were made more stringent for curtain wall storefront, dropping down to a 0.40 in Climate Zone 7 and 8. Also in climate for all other, the requirements dropped down to a 0.45 U-Factor, so they were made more stringent there. So that's for glazing U-Factor. Now when we're going to get into solar heat gain coefficient requirements, and the solar heat gain coefficient is really it's how much solar gain is allowed to pass through a window. The lower the solar gain, the lower the cooling loads are going to be in that space. So if we're down in Las Vegas, for example, we don't want a lot of solar gain passing through the window, primarily because it's going to increase our cooling load significantly. But in some areas, in colder areas of the country, we actually might want a lot of solar gain passing through. So it actually we might get some passive solar benefit for a lot of gain coming through during the winter time. So the hotter the climate, you can see in Climate Zone 1, for example, the first column of solar heat gain coefficient, PF, which is projection factor less than 0.25, the requirement is a 0.25 SHGC. That means that only allows 25% of the solar gain that strikes that window to pass through the glass. When we go to the other extreme and the same solar heat gain with the same projection factor, we'll talk about projection factor in a bit. In Climate Zone 8, the solar heat gain coefficient requirement is a 0.45. Essentially what that means is it allows 45% of the solar gain to pass through. In the 2006 code, this was actually I believe it's NR, no requirements in the colder climates. What we're seeing right now for cold climate buildings is actually there's a lot more cooling and air conditioning in those buildings, and so actually solar gain does a good thing to reduce some of the solar gain, to reduce the cooling load in some of the colder temperature buildings, or in colder climate zones. Now, we can meet the requirements in a couple of different ways for solar heat gain coefficient. One is we can go ahead and install the window with the right properties, the 0.25 or the 0.4. The other way we can go ahead is and put an overhang on that window. And the solar heat, the projection factor is just a measurement of the overhang. It's the ratio of the overhang to that piece of glass. So how well that projection factor is actually going to shade the window. And we'll cover that in the next couple of slides, but I kind of want to walk through the rest of this table just to show you how the table works. If we have an overhang, you can see in Climate Zone 4, for example, there is no requirement for an overhang with a projection factor of 0.25 to 0.50. So you can see the NR starting there. If you have a longer overhang of greater than 0.5, again, starting in Climate Zone 4, you do not have a requirement for solar heat gain coefficient. If you want clear glass, if you have display glass for retail space, for example, and you want relatively clear glass and not tinted or glass with a low-E coating on that, installing a permanent overhang over that glass will actually allow you to have relatively clear glass, so you can actually see through the display windows into that building. So that would be one reason why you'd want to go ahead and put in a higher SHGC glazing, then offset the energy loads on that by putting on an overhang over the glass. For skylights, you're limited to 3% maximum of the roof area. Big change between the 2006 and 2009. The 2006 had a criteria for glass skylights and plastic skylights, two different sets of requirements. During the 2009 code change process, this was all put into one set of requirements. So now we just have a criteria for skylights. With skylights, you have both a U-factor requirement and also a solar heat gain coefficient requirement. It's very difficult to shade horizontal glass. So if we're in the climate zone 1, for example, you can see the solar heat gain coefficient requirement there is a 0.35. So it only allows 35% of the solar gain to come through. As you get into colder climates, you can see in climate zone 7 and zone 8, there is no solar heat gain coefficient requirements for those because solar gain in those climates is actually not a bad thing. So this is, so you now have both a U-factor and also an SHGC requirement for skylights, and it's all kind of a one-size-fits-all. It's going to be for both plastic and also for glass skylights. Cover a few more distinctions on how to calculate that window-wall ratio, for example. We're talking about a 40% window-wall ratio, and this means we take the total gross wall area and the total gross glass area in that building, and you divide glass by wall to come up with window-wall ratio. And the wall that we're looking at is above-grade walls. So if we have a glass building like the Mandalay Bay, for example, that's probably going to be more in the 75 to 80% glass-to-wall area or window-wall ratio range. If we have a big box store, for example, that might be down less than 10% of the window-wall ratio or glass-to-wall area ratio. So this is the one calculation you do need to do to determine how much glass you actually have in that building, and can you use Chapter 5 of the IECC, or do you need to go into the ASHRAE Standard 90.1 2007, or do you need to use the system performance approach? Talked about some of the different site-built windows. The upper right-hand corner is showing a framing materials other than metal with or without metal reinforcement or cladding. So this would be an example of a building that they just use manufactured windows and install those windows. So a vinyl frame window, for example, that would look a lot like a residential scale window is used in this particular building. That's what would classify for this category. Curtain wall. A curtain wall is really more of a non-structural wall, glass wall system in a commercial building. You can see the curtain wall in the round section of this particular building up here, and there will be a specific NFRC or U-factor requirement within the table that you'll need to get an NFRC rating on this product, and or a National Fenestration Rating Council rating in order to show that your curtain wall product actually meets the requirements within the code. Other types of glass include storefront. Upper left-hand corner is a typical storefront glazing that you might find in a strip shopping center. That will have this is a site-built window that will have a U-factor to meet. And again, this particular product will have to have an NFRC rated product installed to ensure that it actually meets the U-factor requirements within the code. Entrance doors, the entrance doors that we looked at, the U-factor requirements are not as stringent as the curtain wall storefront, primarily because they do need to take abuse. So the entrance doors showing in the bottom right-hand corner, the U-factor requirements on these entrance doors are not going to be as stringent as the curtain wall storefront requirements or some of the other types of requirements in the code. Operable windows for metal frame. These are showing metal framed operable windows. This falls underneath the all other category, and this is kind of that catch-all category that if your glass doesn't fall into any of the other categories, you have to go ahead and use. So that's going to include operable windows, fixed windows, non-entrance types of doors that are still glass will fall underneath, again, this catch-all category of all other, and that will have specific U-factor requirements. Now, I do want to say that even though the U-factor requirements on this type of fenestration for all of these categories varies based on the type, the solar heat gain coefficient requirements are going to be the same from category to category. So if it's a 0.40 for one type of glass, it's a 0.40 for all glass on that particular climate zone. There's no distinction on that. When we looked at, I briefly described solar heat gain coefficient. So just to give you an example of some of the different types of solar heat gain coefficient, the upper right-hand corner, the MGM Grand, has an SHGC of about 0.14. As roughly as we can calculate, so that only allows 86, that actually blocks 86% of the solar gain from coming through that glass. The Mandalay Bay on the building down below it has a solar heat gain coefficient of 0.12 roughly, so that allows 12% of the solar gain that strikes the Mandalay Bay to actually pass through. The glazing down in the bottom right-hand corner, the tinted glazing down there is probably somewhere between a 0.3 to 0.4 based on the glass properties, the number of panes of glazing, the type of tint and things like that. Again, this would be an NFRC-rated product. If I take this glass into a default table, which is also included in the IECC, we will not get as low of SHGC range. So this would have to be a tested value. This could range, anywhere from a 0.3 to a 0.45, for example, based on the type of glass you put in, the type of tinting, that type of thing. So again, all we're looking at is how much solar gain is blocked through that glass. The more that's blocked, the more it reduces the solar gain on that building. Now, there's always been a question about what do you do with if you want to daylight a building, and you can actually get glass, not a code requirement, but you can get windows that have a low solar heat gain coefficient value, but a high visible transmittant or visible light transmittant value. So it blocks the solar gain, but it does let the visible light spectrum through that glass. Now, this is not a code requirement. But this is something to think about if you want to do daylighting or lighting the inside of the building using natural daylight from the outside. We talked about, and we used the term projection factor earlier, and a projection factor is essentially the ratio of the overhang to the glass. So if I look at this diagram, I have two values. I have my A value, or the horizontal distance between the surface of the window to the farthest most point of the overhang, and my B value, or my B dimension, from the bottom of the window to the bottommost point of the overhang. My projection factor is calculated by dividing the A dimension, or my horizontal dimension, by my vertical dimension to come up with a number. So, for example, if my horizontal dimension is 4 feet and my vertical dimension is 6 feet, I divide 4 by 6 and come up with a projection factor of 0.67 if my math is correct. I then take that projection factor back into the solar heat gain coefficient table that we were looking at earlier under the fenestration, and that would be greater than a 0.5 projection factor, and that would then allow me to install a piece of glass with a less stringent solar heat gain coefficient. So based on the climate zone, instead of, for example, putting in a 0.25 for climate zone 1, I can actually install, let me pull up the table here, I can actually install a 0.40 solar heat gain coefficient for climate zone 1 with that kind of an overhang on it. So that allows me to do a trade-off to get relatively clear glass by installing the overhang. And for example, again, if we're looking at a retail space, so if I want to use relatively clear glass, this would allow me to get relatively clear glass versus putting on something with a 0.25 SHGC, which is a fairly hard glass to see through. So this is how projection factor plays into the compliance with the code. Now, the overhangs for this they should be a permanent overhang on the building. An awning that retracts, for example, during times of the year is not considered a permanent overhang, so it actually should be a permanent fixed overhang on that building in order to count for compliance with the code. Okay, that ends the installation and glazing requirements. Now we're going to get into the mandatory requirements. We only have a little bit of material left to cover. We'll get into the mandatory requirements, though, and the first of the requirements is going to be for air sealing. And the requirements basically say you must caulk gasket or weather strip any penetration in the building envelope. With an approved sealant method, it actually has the ability to expand and contract if it's connecting to similar materials. For example, wood and concrete. They both expand and contract at different rates, and the product you use has to be pliable enough that it doesn't break or break down over a period of time. What they're finding right now is actually sealing up the building for commercial buildings does play into a part for energy efficiency for commercial buildings. Some states, for example, already have requirements for continuous air barriers, like the state of Massachusetts. So it's essentially getting the building sealed up. We're already bringing in air into the building in our ventilation system, and so bringing in infiltration air, unwanted air, makes the mechanical system have to run that much more in order to offset the loads for infiltration. So seal up the building envelope as best possible. There's also requirements if you have dampers that are integral to the building envelope. In this particular case, the picture you're seeing up here, there are dampers into the building envelope. They're release dampers, because if you bring in economizer air, for example, and pressurize the building, you need to relieve that air, and a release damper is one way of doing it. But you want these dampers shut when the system is not working. That's the whole thing. So you have a couple of options for motorized dampers, or for dampers rather, for integral to the building envelope. One is they can be a Class 1 motorized leakage-rated damper, or for buildings less than 3 stories or height, they can be a gravity damper that are closed when not needed or not in use. And again, we're just trying to reduce the amount of infiltration air that comes into the building, and this is one way of doing it. Other ways of reducing infiltration air for conditioned loading docks. The code requires loading docks with Weatherseals. So when you back the tractor up into the loading dock, it actually seals around the back of the tractor and reduces the infiltration load going into that loading dock. And this will reduce the energy needed to keep that loading dock at the temperature. There are no set requirements for loading dock Weatherseals. There's no ASTM testing and that type of thing. It's in the code. It basically just says use a Weatherseal or a loading dock Weatherseal on this one, but you're trying to reduce infiltration for this particular building. One of the requirements that's been somewhat contentious since it came into the code is a requirement for a vestibule, and a lot of designers have actually gone into ASHRAE 90.1 to get out of the vestibule requirements for particular building stock. And that's worked well for them because they've complied with the envelope requirements for 90.1 and then the lighting and mechanical requirements in Chapter 5 of the IECC. Now, if you decide to go into ASHRAE 90.1 2007 to comply with to basically get out of the vestibule requirements through one of their exemptions, you will now have to comply with all of ASHRAE 90.1. So the allowance has been somewhat taken away, but let's focus right now on just what the requirements are within Chapter 5 of the IECC. What the code says is that if you have essentially the primary entrance door leading from a space greater than or equal to 3,000 square feet, that door must have a vestibule on it. And the doors we're really focused on here are the doors where the general public and the people that work in the building enter and exit that building. This is really the primary focus of the doors that we're focused on. Now, the requirements for the doors is the doors have to have self-closing devices, so an automatic sliding door would work, or a swinging door with a self-closing device would work on that. And the doors also have to have the ability, the vestibule has to be designed so that both doors do not have to be opened at the same time to exit and enter the vestibule. So, for example, in the picture I have here, the door leading from the conditioned space and the door leading to the outside at the other end of the vestibule would not have to be opened at the same time in order for me to pass through. The whole goal of a vestibule is to create an airlock. So you would enter the vestibule, have the door shut behind you, and then exit the vestibule and have the doors open in front of you to exit that building. That creates that airlock. The 3,000 square foot requirement on here, essentially, there isn't a good definition in the IECC, but probably the best one I can give you right now is the space is defined by surrounding by floor-to-ceiling partitions. That would define the space. If you have a entrance into that, and we show an entrance into this particular space, if there's a door on that entrance, I would not count the square footage on the other side of that door as part of the conditioned space. If there's no door on that entrance, or that opening between what might be a less than 3,000 square foot space and the space next to it, I would go ahead and count that because you will have heat transfer between the two spaces. So this has been unfortunately, the vestibule requirement in the code is not as clear as it should be. I know it's being worked on through the code development process, and hopefully we'll have a little more clarity in future versions of the code. Some of the exceptions: buildings in climate zones 1 and 2 do not need a vestibule. Doors from a guest room or dwelling unit. Remember, this requirement is also for high-rise dwelling units. So if you have a guest room for a hotel motel, for example, that's with a door leading into a space greater than or equal to 3,000 square feet, or a dwelling unit, you're exempt from that. Doors used primarily for vehicular movement, material handling, and adjacent personnel doors are exempt. Also, the one bullet I don't have on here are revolving doors. If I have a revolving door, for example, in a lobby of a hotel motel, you would not have to have a vestibule on that particular door. So there are some exemptions on the vestibules that are in the IECC right now. Last but not least are the mandatory requirements for can lights or recessed lights that are actually in the building envelope itself. So this is not going to be a can light and a drop ceiling, because remember, the drop ceiling cannot be part of the building envelope. This is going to be a can light if I have a sheetrock ceiling with insulation on the top of that, and I put my can lights into that sheetrock ceiling. Then the can light is going to have to be type IC rated and sealed and gasketed between the can itself and the sheetrock. And it also, the type IC rated means that it's rated for insulation contact, and the airtight means that the can will not leak. Basically, it won't leak air through the can itself, or it has a very minimal amount of air leakage. In this case, 2 CFM of air movement from conditioned space into the ceiling cavity. So drastically reduces the infiltration through that can, and it also allows you to insulate right up around that can. That means that when you're insulating the ceiling assembly, you won't have spaces where the can is inserted. If I had a non-IC rated can light up there, I would have to hold my insulation back a certain distance away from the can. So I'm actually would have to eliminate some of the insulation in that ceiling. This would allow you to insulate all the way up around that can. But again, this is only for can lights that are in part of the building envelope. So this would be an insulated ceiling with a sheetrock ceiling assembly, for example, and the can would be inserted in that, not a drop ceiling. So I definitely want to make that distinction. So what have we talked about today? We've talked about some of the changes in the R value requirements for the opaque envelope requirements. I've showed you the new U-Factor table for assemblies and a way to meet the requirements if your assembly does not quite meet the R value requirement. We looked at the changes in the fenestration requirement. One of the biggest changes again on that was the skylight requirements are now, instead of plastic and glass, are going to be just one set of requirements for all types of skylights. We've talked about air leakage and the importance for air leakage and sealing up the building envelope. We looked a little bit about vestibules and meeting some of the vestibule requirements, and we also talked briefly about the weather seal that's required for conditioned loading docks. This ends my discussion today, and I hope if you have any questions that you'll feel free to ask them. Thank you.
Well, thanks very much, Eric. I'm actually going to jump in and put a slide up on the screen for all of you that are interested in receiving AIA credit or generating and printing a certificate of completion for yourselves. Please write down the link that's appearing on the screen right now and go to your browser at the end of the event today, type that link in, and follow through the pages, and you'll be able to submit your AIA information to us and or generate and print a certificate of completion. So thanks again for participating in today's webcast brought to you by the U.S. Department of Energy